everyone, this video is all about titration, in which you are already familiar and you have already encountered this during your lobster simulation. But here on this video, we will be integrating some common problems that you will be encountering in a laboratory setting. Quantitative studies of acid-base neutralization reactions are most conveniently carried out using a technique known as titration. And we can define titration as a solution of accurately known concentration called a standard solution is added gradually to another solution of unknown concentration until the chemical reaction between the two solutions is complete. So if we know the volumes of the standard and unknown solution used in the titration along with the concentration of the standard solution, we can calculate the concentration of the unknown solution. So sodium hydroxide here is the most common base that is used in a laboratory because it is cheap and easy to obtain and process. So there is a difficulty in obtaining a pure solid NaOH because it absorbs water from air. And its solution, or the aqueous form of NaOH, reacts with carbon dioxide. In order for us to use the sodium hydroxide in an analytical work, we have to standardize that, and we can standardize an NaOH solution by titrating it against an acid solution of known concentration. So for the acid solution of known concentration, we are commonly using, for the standardization of NaOH, we are using the KHP, or the potassium hydrogen phthalate, for which the molecule formula of this one is KHC8H4O4, and the molar mass of this one is 204.2 grams. The reaction between the KHP and sodium hydroxide is this one. This is the reaction. Plus sodium hydroxide, you will yield these products here. So the procedure for titration can be illustrated in this picture here. The first thing that you need to do is known amount of KHP, or potassium hydrogen phthalate, is transferred to an Erlenmeyer flask, and some distilled water is added to make up a solution. So it depends up to your teacher, and you will put that here. This is the Erlenmeyer. You will add here the KHP and then some distilled water to make up the solution. And then the next thing that you will do, you will add a sodium hydroxide solution carefully or gradually to the KHP solution from a burette until we reach the equivalence point. So this is where you will put the sodium hydroxide solution here until gradually. Okay, this is the setup. You have here the support stand, the burette holder. This is the burette and this is the flask. So to control the flow of the NaOH solution, you will be rotating this holder here in of the burette. So we have mentioned here the equivalence point. Equivalence point, where is that? Let us define that. This is the point at which the acid has completely reacted with or been neutralized by the base. So this equivalence point is often signaled by a sharp change in the color of an indicator in the acid solution. This is the common indicator. So indicator are substances that have distinctly different colors in acidic and basic media. These are the common acid-base indicator table. We have here the methyl orange, bromophenol blue, thymol blue, phenolphthalein, and alizarin yellow. This is the pH of these indicators, and the color that will change in a weak acid. For conjugate base, for phenolphthalein, this is the most common indicator that is being used in a titration, which is colorless in a weak acid, and it will have a light pink, not this dark. So for base, and so at equivalence point, all the KHP present in has been neutralized by added NaOH, and the solution is still colorless. However, if we add just one more drop of NaOH solution from the burette, the solution will immediately turn into pink. So this is just like this one. So this is your starting point, colorless. But if you will add, this is the KHP solution, right? And then if you will add an NaOH solution, it will add some color, and then adding more, this is the ending point or the equivalence point. And if you add more, that is overshot, we call it, or you exceeded the molarity. So this one therefore is not accurate. This is the most accurate and most correct titration, just like this one. Overshot, endpoint, light pink, very light pink, and this one titration. So this is an advanced setup, but if you don't have the apparatus, this will do, and it requires a very much advanced control skill to control the amount of NaOH droplets Then, so as you can see, there is a pH meter reader, and then we have here 0.1 NaOH solution, the NaOH. So if you don't want to add gradually, so most often they are adding that here. Then you can use glass tube such as this one to control the flow, and by rotating the handler here to control the flow of the NaOH solution here. And here is a stirrer, so just in case you don't want to manually swirl. So here are the colors for phenolphthalein. You have here light pink, this is the equivalence point. And here, if you reach the dark color, that is an overshot. Same with bromothymol blue here, and metal orange. Then, the neutralization reaction between NaOH and KHP, just like what I discussed earlier, it is one of the most simplest type of acid-base neutralization known. Suppose though that instead of KHP, we wanted to use a diprotic acid because the KHP is a monoprotic acid. When we say monoprotic acid, let me write that monoprotic, meaning to say the acid can donate only one proton. But in diprotic, it can donate 2 protons. So we have here 2 NaOH. This is the reaction of sodium hydroxide to a diprotic acid, which is, for example, a sulfuric acid. So in 1 mole of sulfuric acid, to yield this product, you will need 2 moles of NaOH. Because 2 moles of sodium hydroxide is equivalent to 1 mole of sulfuric acid, we need twice as much sodium hydroxide to react completely with a sulfuric acid solution of the same molar concentration and volume as a monoprotic acid like the HCl here. This one is monoprotic rather. On the other hand, we would need twice the amount of hydrochloric acid to neutralize a barium hydroxide solution. So remember that in calculations involving acid-base titrations, regardless of the acid or base that takes place in the reaction, keep in mind that the total number of moles of hydrogen ions that have been reacted, H+, at the equivalence point must be equal to the total number of moles of OH ions. So they must be equal. So you have to balance your equation therefore. And remember that acid-base titrations involves transfer of proton. Here are examples of problems involving monoprotic titration or monoprotic acids. In a titration experiment, a student finds that 23.48 milliliters of a sodium hydroxide solution are needed to neutralize 0.5468 grams of potassium hydrogen phthalate. What is the concentration in molarity of the NaOH solution? So, the strategy here is we want to determine the molarity of the sodium hydroxide solution. What is the definition of molarity again? So, molarity is defined as the moles per liter of solution. So, the volume of NaOH solutions is given in the problem here. That is given, which is 23.48 milliliters rather. Therefore, we need to find the number of moles of NaOH to solve for molarity. So, we have to know first how many moles of KHP are contained in 0.5468 grams of KHP. So, to determine that, we have this formula or solution rather, 0.5468 grams of potassium hydrogen phthalate multiplied to the 1 mole of KHP. And we all know that the molar mass of KHP is 204.2 grams. Then, cancel the gram unit here. Perform the operation. Divide that. You will have 2.678 times 10 raised to negative 3 mole of the potassium hydrogen phthalate. And then, the next thing that we need to do is to determine the molarity of the sodium hydroxide solution. To determine that, because 1 mole of sodium hydroxide, there must be 2.678 times 10 raised to negative 3 mole of NaOH in 23.48 milliliters of sodium hydroxide solution. Finally, we need to calculate the number of moles of NaOH in 1 liter of the solution, such as this one. So, molarity of NaOH solution is equivalent to the 2.678 times 10 raised to negative 3 mole of NaOH, and then over 23.48 milliliters of solution. So, multiplied to 1,000 milliliter solution over 1 L of solution. That is 0.1141 mole of NaOH per liter of solution, or 0.1141 molarity. This is the answer. So, if you will ask why we have here again, okay, but this is from here, and then you will have here this one. This is the relationship based on the equation of the NaOH. Where is that? where is that? Let me get back here. This one, we have here 1 mole of NaOH and 1 mole of the KHP. So therefore, whatever the amount of the moles of the KHP in the reaction will have the same amount to the NaOH. So that is why you will have here this value. 2.678 times 10 raised to negative 3 mole of potassium hydrogen palate is equivalent to the 2.678 times 10 raised to negative 3 moles of sodium hydroxide. Because 1 mole of KHP is equivalent to the 1 mole of NaOH, there must be 2.678 times 10 raised to negative 3. This is based on the solution, not the pure form of the NaOH, rather the solution. Another problem we have here. So this problem is an example of titration involving diprotic acid. But whatever acid that is, whatever monoprotic, diprotic, or triprotic, all you need to do is perform the operation and determine the molar concentration. So the problem is how many milliliters of a 0.610 molarity sodium hydroxide solution are needed to neutralize 20.0 milliliter of a 0.245 molarity of sulfuric acid solution. So we want to calculate the volume of sodium hydroxide solution from the definition of molarity, because molarity again is moles per liter of solution, and if you will manipulate that, is molarity per moles of liter of solution. So if you will manipulate that, that is liter. So you are being asked of the liter. So that is liter is equals to the mole over the molarity. So let us perform this. From this equation of the neutralization reaction of NaOH and sulfuric acid here, where is that? Later. Let us solve here first. So we have to determine first the moles of sulfuric acid, that is 0.245 mole of sulfuric acid over 1000 milliliters of solution times 20.0 milliliter of solution, because although the mole is given, but that is in 20.0 milliliters, so you have to convert that first into liter. So converting that, cancel the solution, cancel the units here. You will have 4.90 times 10 raised to negative 3 mole of sulfuric acid. So, we all know from this equation, this one here, we all know that 1 mole of sulfuric acid in a reaction is equivalent to 2 moles of sodium hydroxide. So, that is 2:1. So, therefore, if that is 1 mole of sulfuric acid is equivalent to 2 moles of sodium hydroxide, therefore, you have to get twice the mole. 2 times 4.90 times 10 raised to negative 3, 2 times the mole of sulfuric acid is equals to 9.8 times 10 raised to negative 3 mole, and then you can get the volume of sodium hydroxide na. So to get that, that is 9.80 times 10 raised to negative 3 mole of sodium hydroxide over 0.610 mole of liter solution. Then, performing that, you will have 0.161 liter or 16.1 milliliter. So, you can convert that into milliliter for easier measuring of the volume. By moving, of course, by moving the 0 places. 3 movements to liters here. 1, 2, 3. That you will have 16.1 milliliters here. And then, next, redox titrations. So, as mentioned earlier, acid-base titrations is all about the transfer of protons. Here in redox, it involves transfer of electrons. And if in the acid-base neutralization, you just have to react an acid to a base to neutralize. Here in redox titrations, you have to titrate an oxidizing agent against a solution containing a reducing agent. So, when we say oxidizing agent, where is that? Oxidizing agent gains an electron. And then, a reducing agent loses an electron. Monoprotic acids examples. Examples of oxidizing agents and examples of reducing agents. Okay, so like acid-base titrations normally require an indicator as well that clearly changes color. So in the presence of large amounts of reducing agent, the color of the indicator is characteristic of its reduced form. So for example, here the indicator assumes the color of its oxidized form when it's present in an oxidizing medium. At or near the equivalence point, a sharp change of the indicator's color will occur. So the two common oxidizing agents are potassium permanganate and potassium dichromate, KMnO4 and KM. Wait. KMNO4 and the potassium dichromate, which is K2Cr2O7. So this is the purple color, and if that will be oxidized, that will be light pink, and this one is orange to yellow, and that will be a green in color. So redox titrations require the same type of calculation based on the mole method as well of the acid-base neutralization. Here is an example of the problem involving redox titrations. 16.42 milliliter volume of 0.1327 molarity of potassium permanganate solution is needed to oxidize 25.00 milliliter of a ferric sulfate solution in an acidic medium. What is the concentration of the FeSO4 solution in molarity? Wherein the net ionic equation is this one. So for redox reaction, you will be encountering the ionic charges. Unlike the acid-base neutralization, it just have the aqueous, liquid, and gas subscript. But this here in redox, you will have the charges. It seems complicated, but it just denotes the charges. For the solution, we want to calculate the molarity of the FeSO4 solution from the definition of the molarity, which is molarity is equivalent to the moles per liter of solution. So here is the solution. The volume of the FeS2O4 is given in the problem. Therefore, we need to find the number of moles of FeSO4 to solve for the molarity. So from the net equation here, we can determine that here. So the number of moles of KMNO4 in 16.42 milliliter of the solution is this 1 moles of KMNO4, 0.1327 KMNO4. We have to convert that 1000 milliliter of solution times 16.42 milliliters. So you will have here, cancel that, cancel. You will have 2.179 times 10 raised to negative 3 moles of KMNO4, then 4 moles of FeSO4. You have 5 moles here, right? 5 moles. So that is 2.179 times 10 moles of KMNO4 times 5 moles of FeSO4. Then cancel. You will have 1.090 times 10 raised to negative 2 moles of ferric sulfate. Then for the molarity of the FeSO4, you have this 1.09 times 10 at the numerator, this one here, and then the milliliter of the solution, which is 25.00. Then convert that into liter here, times 1000 over 1 liter of solution. You have to cancel the milliliters, and then you will have 0.4360 molarity. This is the answer for the redox titrations. So that is all for titrations.